So now we're looking at PQ question 8. We are given that y equals to ln 1 plus sin x. We want to show that EY equals to show that EY dy dx equals to cosine x. Right, so let's start on part 1. Okay, so very simply we know that y equals to, just write it out first. This is ln 1 plus sin x. Okay, dy dx, remember you differentiate. Let me just quickly write out the formula aside. Remember that if we were to differentiate ln of fx, right? I hope you still remember this is just equals to f prime x over fx. Okay, so dy dx is equals to differentiating the f prime over f, so give us cosine x over this is 1 plus sin x. Okay, then e to the power of y equals to cos x, so it will be quite easy. So it was e to the power of y. E to the power of y, given that y equals to ln, so e to the power of y will just be e to the power of ln, which is nothing, we just cancel out. And okay, then dy, so you can see that e to the power of y multiplied by dy dx will just be cosine x multiplied by 1 plus sin x multiplied by 1 plus sin x, and they will all cancel off. And you can see here, part 1 is done, you have shown. Part 2, okay, we need to show that part 2 we need to do all the way up to the third derivative, d3y dx cubed, d2y dx squared. Okay, so here, highlight, we need to do some implicit differentiation. Okay, then we have let's differentiate our part 1 equation one more time. This is e to the power of y dy dx is equals to cosine x. Okay, differentiating this one more time. Keep differentiate left. We have e to the power of y dy dx. Okay, multiplied by dy dx plus, now we keep the e power y. We differentiate this. This e power y d2y dx square. Okay, and this is cos x, so if we differentiate cosine x, that will give us a negative sin x. Okay, there is e power y dy dx square. Okay, so if you're not sure of this part, you just remember, okay, that remember if when we differentiate e to the power of fx, right, that gives us f prime x, e to the power of fx. Okay, so in this case, our fx is just like a y. Our fx is just like y. So if we erase fx and we put y, then this is the same as dy dx, right? This is e, this will just be your y. That's why we have this. Okay, this is nothing but implicit. So implicit differentiation, we just treat the y as a function of x, and then dy dx as f prime. Okay, so that's all. Then next, okay, we just go on to carry on the equation. It's e power y d2y dx cubed equals to negative sin x. Okay, so we are not done. We need to go on and find the third derivative again. Okay, so one more time. This will be differentiating this. This is e power y dy dx again. So this give us a dy dx multiplied by dy dx squared. So it's dy dx cubed plus. Now I keep the left side. I differentiate the right. This will give me e power y. So I differentiate this, right? This is like f prime x to the power of 2. So it's a 2 dy dx to the power of 1 multiplied by d2y dx squared. Okay, next one, e power y d2y dx squared. E power y d2y dx squared. We differentiate this one more time. This will give us e power y dy dx, right? And so e power y dy dx, that comes from differentiating this. And now we keep this. This is d2y dx squared. Okay, and we're not done. Now we need to differentiate our d2y dx squared. That will give us d3y dx cubed multiplied Okay, this will be equals to 1. Okay, so y equals to, so with that you can form an equation. So your fx is equals to x. So remember it's a f of 0, so because it's just 0, the constant. So it's just x minus half x squared plus 1 over 6 x cubed. And that is all. Okay, approximately that's as x minus half x squared plus 1 over 6 x cubed. Okay, what's the last question? The last question is that we need to show that cosine x. So the last question, we need to show that cosine x gives us 1 minus x plus x squared over 2. How do we do that? Cosine x over 1 plus. So what does it look like? Can you see that this is nothing but the derivative of this? It looks like the derivative of this, right? So this is cos x over 1 plus x. So what do we do? If we have the Maclaurin expansion for this, okay, so we have the Maclaurin expansion for y. Can we also find the Maclaurin expansion for dy dx? Can, right? So we just, you know that if y is equal to something x plus x squared plus dot dot dot. So if you differentiate y to get dy dx, similarly if you differentiate this Maclaurin, this expansion, you can also get the Maclaurin expansion for dy dx. Okay, so with that, that's what we're going to do. Okay, then you know that your y equals to ln 1 plus sine x. Okay, this is equals from your earlier part. You have found that this is approximately x minus half x squared plus 1 over 6 x cubed. Okay, if you do dy dx, your dy dx is actually what they want in the question, which is cosine x over 1 plus sine x. What's the Maclaurin expression for this? I just differentiate the earlier part. Then this will give me, differentiate x, I get 1. I have x minus x, differentiate x squared to 3 power x, so this plus half x to the power of 2.